Let's start. So today we'll finally be talking about entanglement in the ground state of local Hamiltonians. We'll use what we've learned from free fermions to draw some general conclusions. And so I will be quoting a number of facts, some of which you have to believe, some of which you'll test in the tutorial today. But you have all the tools available with what we've learned about Julia to actually test everything I'll say today. Very good. So we want to talk about scaling of entanglement in ground states. We start with these free fermions. And first, I want to consider one-dimensional systems with a Hamiltonian H with energy gap. Okay, so we define the energy gap as the difference of energy between the first excited state and the ground state. Okay. And we actually define this in the limit of a very large system. So if you may see that for a finite system, you have a gap, right? This is positive. This is some finite number. But as you increase the system size, this gap may close. Now we are interested in the case where in the thermodynamic limit, so in the limit of an infinite system, we still have a finite gap, okay? And in that case, we can draw the dispersion relation. I'll do this here. So let me draw energy as a function of k, momentum. This is k. And what we're talking about is the case where in the continuum you have a continuum, in the thermodynamic limit you have a continuum of momenta, and we still have some finite gap here. This is our delta E larger than 0. And examples of this could be the Ising model that you dealt with, or the Majorana model that you dealt with an H, which is, there was this parameter H in the Hamiltonian, which is going to be, say, for instance, 1.1, or different from the critical value, which is 1. Okay? So you can go and test whatever I will say next. Actually, you'll see it in the tutorial today. So once we have such a Hamiltonian with this gap, we can ask a number of questions for the ground state. Now I'm going to talk about the ground state. I'm going to plot two different things for the ground state. First, I want to talk about correlations. And then I want to talk about entanglement entropy. Okay. As a function of, I'm going to plot this as a function of the logarithm of L. So what I'm thinking here is that we already take n, the system size, to infinite. And L is size of region A, right? We divide our system into two pieces, A and the rest, and we trace out the rest. And we can ask questions about this region A, or in the case of correlators, simply how much is a correlator from one point to a point which is L sides apart. Okay, so if I have a gap system, then what you can see is, let me plot here log of a correlator. So this is a log-log plot. And for correlations here, directly you could take a C of this correlator. It could be something as simple as you take your correlation metrics with the indices M and M plus L. This would be something that would give you correlations in the system. Okay, you take these correlation metrics. You ask how a mode, so this is about the expectation value, say, or is related to the expectation value of, say, psi M1, psi M plus L2. Let's take this one, right? So we can plot this as a function of L. The system is translation invariant, so M does not enter. This does not depend on M, it only depends on L. And what you will see is actually something like this. You will see a behavior that looks like that. Okay, so what we see here is this is a log-log plot. What we see, what we're going to focus on is this part here, which actually says that this correlator, C of L, goes asymptotically for large distances as it decays exponentially with L. Okay? So if we have a gap system, correlations decay exponential. We have an exponential decay of correlations. And then this will happen. So we see first some other behavior, but then it tends to this exponential decay. And then this occurs, roughly speaking, around what is called the correlation length. So there is a quantity, Xi, which is the correlation length. This is a length scale after which you see that the correlations decay exponentially, and with the correlation length also appears in this exponential decay. Very good. So that's what we see when we look at two-point correlators. You can test this. And if we look at entanglement entropy, what we observe, so now I'm going to plot entanglement entropy here. What we observe is S of L. We observe some behavior that looks like this. First, we have a logarithmic scaling, and at some point, it saturates to a constant. Okay? So, and I'm going to focus. So what we say is that the entropy goes to a constant. Okay, so this is a gap system, and there is, again, some place where this happens, roughly speaking, and this would be, again, when L is on the order of the correlation length in the system. Okay? Good. So these are statements that you can check. What I want to, but the point is that we are testing this for free fermions, but this is a very general statement that we observe in one-dimensional systems when we have a gap in the Hamiltonian. Now, we could also test what happens in gapless systems. So let me consider now a gapless Hamiltonian, gapless H. So what we're saying here is that instead now the dispersion relation decides that there is no gap. Okay, there are zero modes in the thermodynamic limit. And then for this case, so examples, this would be again Ising model, examples that you've been playing with, or Majorana model that you would consider, which were dual. And that would be for H equal to H critical, which is 1. And if we plot again the same properties here, if we look at correlations, or if we look at the scaling of entanglement entropy, what we'll see this time is a power law all the way. So we'll see that the correlations this time obey power law. Okay, decay as some power of the distance. And the entanglement entropy will follow a logarithmic scaling at all distances. Okay? And obviously you can understand this second case as what happens in the first case in the limit where the correlation length goes to infinite. So what we are saying is that there was some initial behavior which happened to be approximately logarithmic, which was corrected into a constant at the correlation length. But if we keep pushing the correlation length away, larger and larger, we'll end up with just having this pure behavior. Okay, so these are two parts of the same picture. Very good. So what else can we say? Okay, so it turns out that we've been looking at other models. So let me consider another gapless model. And in that case, and this could be the XX model that you have also been studying, or the fermionic, the model with quadratic and fermionic operators that we've been looking at, which again are dual. through Jordan-Wigner transformation. And what we see in this case is that, I don't know if you remember, there was some dispersion relation. It looked like that, but once you decide to change the sign of these particles, so these states are occupied in the ground state, so let's change to antiparticles, and what we see is that the dispersion relation ends up looking like this. I just took these negative energies and made them positive, since these states are going to be occupied anyway. And so we see the dispersion relation has this form now. And then if we plot again correlations and entropy, what we see is, again, some power law. So this is correlations decay as 1 over L with some new power, prime. And the entropy, so log L, log of the correlator, okay, entropy. And the entropy follows, again, a logarithmic behavior, okay? But if we compare the entropy that we have here and the entropy that we have here, if we look carefully, what we see is that this entropy is actually not just some logarithm. It's 1 over 3 log 2 of L. Whereas here, if we look closely, we see a 1 over 6 log 2L. Okay? So what we start to see is that there is some very concrete number that appears in front of the logarithms. And actually, what you could do, you can really do this if you want, is to play around with this fermionic model. You can add next to nearest neighbor hopping. So I did this yesterday. And what you get is a new dispersion relation that looks like this. So this is the fermionic model. Okay, plus next to nearest neighbor hopping. Okay, and you get the dispersion relation like that instead. And if you plot, again, you get the power law here. And if you look at what you get here, well, again, you get, for the entropy, a logarithmic behavior, but now it's going to be 2/3 of log 2L. Okay? And if you look at this, there is a pattern here for the critical systems, which is count, so number of zero modes. Okay, we see how many times, for how many values of k, of the momentum k, we get energy equal to 0. Okay? What we see is that there is a relation between the entropy in critical systems, which scales like this. So we have 1 over 6 log 2L. And here we put directly this number of zero modes. Okay? So this is interesting because the entropy is a property of the ground state. Okay? You are only given the ground state, you can compute the entropy from it. You don't need to know the Hamiltonian. It's just a property of the ground state. But the ground state kind of knows how many zero modes are there in the Hamiltonian. Zero modes is a property of the Hamiltonian. Okay? It's a relation between energies of the ground state and other states. Okay? But the ground state somehow knows how many zero modes are there in the Hamiltonian. Okay? And the expression here in general, this was, we have this expression, but actually the one that is valid also not just for free fermions, but in general, is that there is a central charge of the theory divided by log 2, divided by 6 times log 2L. Okay? Okay, so what we're seeing here is the first example where we look at entanglement. Okay, we've computed the ground state, we analyze how entanglement scales, and we learn something about, say, the universality class of the phase transition. We're learning just about we're extracting universal properties of the system just by looking at how entanglement scales. And that's something that we'll see happening over and over.
C over 6 or C over 3?
It's C over 3, thanks. Yes. And then what we had is that for the Ising model, C was 1/2. And for the XX model, C was 1. Indeed. Thank you. Yes. Very good.
Sorry. How do you count the number of zero modes from the dispersion?
I just look at how many times this curve.
Down one?
1, 2, 3, 4.
So after that, it will not.
Oh, yeah, no, we only go all the way to pi, right? Very good. Okay. So then the first conclusion is that we will be able to extract information by looking at important information, universal properties of the system by looking at entanglement. And we'll see this happening many times. But the other observation, maybe the more important one for next week, is that we want to compare with what happens with a random state. By random state, I mean we pick up 2 to the n coefficients here. Right? We can pick up 2 to the n random coefficients. And this ended up being an optional problem in the tutorial 2 days ago, I believe, comparing the scaling of entanglement with a random state. Okay. Yeah. It wasn't there?
It was.
Actually, it was, yeah.
It was. And it was optional, and I don't know how many people did it, but it's not very complicated, and you can do that. And then if you look at the entropy, what we see in this case is, again, we take n going to infinite. Don't try it with a computer. And we just look at L. And we can ask how much is the scaling of the entropy as a function of L. And what we see is that well, the first thing is to remember that there is an upper bound, okay, that says that the entropy of L qubits is at most L. Okay, we saw that the other day. And so if we now take this random state made of random coefficients and we plot it here, what we see is basically something that is very, very close to this bound. Okay, so I'm going to call this S of rand as a function of L. And now we go back to our discussions before, and we plot what the scaling is for ground states, and we have two behaviors. One is logarithmic. Okay, so now I'm plotting this in linear axis, so the log is going to look like a log. So I'm going to say it goes like this. Okay, and I'm being generous. And we also have another behavior, which is constant, which basically consists in you start with logarithmic, and at some point you get tired, and now you are constant. Okay. Okay. And these are ground states of local Hamiltonians. Okay. So really the important conclusion here, much more important than whether we can extract a central charge or not, is that ground states of local Hamiltonians are not very entangled. Okay, and this is really the most important conclusion of maybe the whole course. Yes?
Is there an analytic theorem or something which says this, or is this just observation?
This is an observation based on, well, it's not an observation by one person, it's lots of observations coinciding in this statement. And now we're going to be more precise about how exactly it scales in general and so on. But there might be some theorems supporting partially some of the results about scaling. But usually the theorems are way behind. They prove some maybe that the entropy cannot be linear, right? But we know there is plenty of evidence that it is at most logarithmic. Or maybe there is a theorem that shows that it can at most be logarithmic, but with a huge constant here, which has nothing to do with what we observe. Okay, so there might be some theorems, but but when we want to know how it scales, we really look at examples and accumulation of examples. Okay, so why is this important? Well, let me try to understand possible computational implications. Okay, so what we could have is a product. Let's look at the product state again. Of n qubits. Okay, and what we have in this case is psi1, phi2, phi n. And I can ask, how much is the entropy here as a function of, if I just take L of them, right? And I trace out the rest, I still have a pure state for the L spin. So the entropy here is 0, okay? S of L equal to 0, okay? And on the other hand, if I want to see how many coefficients I need to write this state, I realize I need a couple of coefficients to specify the state of the first spin, couple of coefficients to specify the state of the second spin, and so on. Okay, so 2 coefficients per spin. So say memory or number of coefficients. What I say is that it's order n. Okay, I'm done with order n coefficients. I have completely specified this product state. So no entanglement is good for efficiency in the description. No entanglement, efficient description. All right. Now, down here we have generic or random. I'll call it generic. Okay, I need to push this up. Generic state. By generic state, I mean one chosen with random coefficients, right? I keep repeating this experiment, and I always get the curve that is hard to distinguish with the upper bound. So generic state, then we have psi equal to the sum psi I1, I2, In. Okay. I ask how much is the entropy, and I see that it goes as L. Okay. I look at how many coefficients I need in this case, and I realize it's order 2 to the n. Okay? It takes 2 to the n coefficients to describe this state. And now what we're looking at here is, so we have this one, and I want to look at ground states of local Hamiltonian. Okay? And I still don't know how to express whatever's happening, but there is something happening because the entropy is equal to a constant, or at most log L, which is much smaller than this. Okay? And this is already kind of suggestive that we are in a situation between the generic state and the product state. Okay? We are somewhere in between 0 entropy and maximal entropy. And so the big question that we will answer next week is, what does this imply? Where are we with the complexity of the description? The fact that we have states which are very special, they have only a small amount of entanglement, doesn't mean that we can find an efficient way of describing them. Okay? And so next week we'll answer this positively, we'll say yes. And tensor networks will be the way of exploiting this very particular structure of entanglement. Okay? Very good. So, however, I've only been talking so far about ground states of one-dimensional systems. And now I want to extend this discussion to higher dimensions. And what we'll see there is that basically the same conclusion holds, that ground states are still not very entangled. But it's worth looking also at 2 dimensions, because what we want to do is we want to go to the statement, beyond the statement they are not very entangled. We want to understand why.
Is it possible to look at the previous board?
You want the previous board?
Yeah.
Which was this one, probably. Yeah? Okay. So let's look at 2 dimensions now. And in this case, what we find is that there are 3 different situations of interest. So again, we can have, I'm going to plot here dispersion relation, now as a function of kx and ky. And I'm going to do this 3 times to discuss 3 different cases of interest. Okay? So how do I do this? Yeah. The first case is going to be, again, a gap, Hamiltonian. So we'll see that there is a typical dispersion relation will look like this. Okay? So you have that there is, again, a finite gap here. Between the 0 energy that would be here and the first excitation. Okay? We could have gapless Hamiltonian, which I'm going to call of type 1, where now this dispersion relation went down. And so the gap is 0. Okay? That's also going to be an interesting case. But in 2 dimensions, we can have what I'm going to call gapless 2 situation, where actually what happens is that there is a continuum of 0 modes. Okay? So you could imagine the dispersion relation was going like this, and then after changing particles into antiparticles, we get a dispersion relation like this, where now there is the gap is again 0, but there are many different momenta for which we have 0 energy, whereas here we just had 1. Okay, so let's look at that in more detail. What happens? Let's look at what happens in these cases. So it turns out, and again, this is an exercise that you can do, that if we focus on the entropy as a function of L, S of L, so what we're thinking now here is we are in real space, we have such a system, this is a square lattice, say. Okay, again, n went to infinite, so this is an infinite lattice. But now we look at a region in here of linear size L. Okay, so region A is made of L times L sides. Okay, and we ask how much entropy, what's the entropy of row A? How much entropy do we have in the density matrix describing the region? Okay. In other words, how much entanglement do we have between A, the region A, and the rest of the system? And if we ask this question, if we compute the answer to this question by getting the ground state, computing the reduced density matrix on the region, and then computing the entropy, what we see is that the entropy now is proportional to L. Okay? But how? So what would be S if we try this? What's the upper bound for S of L? Okay. So what's the upper bound in this case that we could have? How much entropy could we have in the region A as a function of L? How many sides do we have in L? In region A, sorry. We have L square sides, so what we're looking here is that the upper bound is L square. When we look at the ground state, instead of L square, we get L. Okay, so again, we are in a situation where we don't have a lot of entanglement compared to how much we could have. Okay, very good. So what happens if we have not a gap system, but a gapless system? So remember, this time now we have the correlation length went to infinite and all these things. We look at the entropy. This would be the behavior, well, the SL that we have for the gap system. And does anybody want to venture how this is going to behave? Logarithmic correction, maybe. Well, one could think that maybe there will be a logarithmic correction, but actually, the entropy scales again proportional to L. Okay? So in gapless case where we have, say this would be a Dirac point, or more generally, what we want to ask is how many, so we could imagine that we have a finite number of zero modes. Okay, so we could imagine a situation where the dispersion relation is more complicated and there are a finite number of zero modes. Here there is only one, but we could have more. Okay, for as long as this is finite, we find this scaling as in the gap case. And when we go to gapless, the case gapless 2, that's where we actually see that the entropy this time goes as L log L. Okay? This requires a Fermi surface or a 1D, how do I want to call this? A 1D Fermi surface, 1D Fermi surface, which amounts to infinitely many zero modes. Okay? So again, what we see is that we're talking about the property of the ground state, but the ground state somehow knows about the full spectrum of eigenvalues of the Hamiltonian. It knows how many zero modes we have. Okay? Very good. So then we are ready to go to the dimensions in general, but I'm going to just write the table here. So we've looked at what do we want to do? Okay, so we have gap systems, and we have gapless systems. And then we have, can be in 1D, 2D, 3D. Okay? And then here I have to talk about two types, so type 1 and type 2 of gapless systems. And what we see is a gap system in 1D. We saw that the entropy was a constant. Okay? In 2D, we've seen that the entropy goes as L. If you do this for 3D, you see that the entropy grows as L squared. So this is always entropy of L goes as L to the d minus 1 dimensions. Okay? Maybe I should write this d equal to 1, d equal to 2, d equal to 3. So this is what we call the area law. Basically, in 3 dimensions, for instance, you could have, again, a cubic lattice of size infinite. And what we're asking is if we have a region of size L times L times L, so this is region A, the entropy of region A does not scale as the size of the region. Okay, the size of the region would be, so if you want S on a random state, if we had prepared a random state of the system and we look at the entropy, this would be L to the 3 this time in 3 dimensions. And we could also think of this as being proportional to the size of the region, how many sites we have in the region. Okay, so we could call this volume law. And this would be for a generic state, random state. But for a ground state, what we see instead as ground state, what we see is that this does not scale with the size of the region, but as the size of the boundary of the region. Okay? So this scales as the size of the boundary of the region. So this scaling with the size of the boundary is what we call the area law. Okay? Very good. And we'll try to understand possible toy models that explain this area law in a minute. Very good. So that's what we have for gap systems. But we also have it here for certain gapless systems. And so there will be a Fermi surface. So I'm going to call this 1. I'm going to call it small. If there is small Fermi surface, and by small, I mean of codimension not 1. So sorry, I'll say that in a second. But so what we'll have here is the type 1 is going to be small Fermi surface, and here type 2 is going to be large Fermi surface. Okay? And what we see is that in the gapless case, we have a logarithmic correction to a constant. Here we have no logarithmic correction. Okay? So if we have a small Fermi surface, in a sense that I'll specify in a second, we still have the area law. And if we have a large Fermi surface, then we have a multiplicative logarithmic correction to the area law. That's what we see in general. Okay? So what do I mean by small or large Fermi surface? Well, in d dimensions, I'm going to call large Fermi surface one that has dimension d minus 1, or codimension 1. Okay? So we just look at here. We're living in we have x and y. We're in 2 dimensions, and we see the Fermi surface has dimension 1. That's okay. It's d minus 1. If we were in 3 dimensions and we look at our dispersion relation, and there is a Fermi surface of dimension 2, then we'll say we have a large Fermi surface. Then we'll have also this logarithmic correction. Okay? And if the Fermi surface has smaller dimension than d minus 1, then we won't see the logarithmic corrections. Very good. So we have this area law, and at most logarithmic corrections to it in some cases. And so the statement that I'm going to make, again, there are no theorems involved in this, is that even though this analysis refer to free fermions, we see that, and for free fermions, you can go and test it. And I think the second homework will be about studying this in 2 dimensions, seeing this logarithmic correction in 2 dimensions. So free fermions are special. We can see this explicitly for arbitrarily large systems, but we have also seen the same behavior in all types of systems, interacting systems. Okay? So we believe that's theorem. No, we believe that this is general. This table applies to, and now I'm going to say all, and then I'll have to take this back, to all types, to all systems. Okay? That if you have ground states of local Hamiltonians in any dimension, they'll obey an area law, or at most logarithmic corrections to the area law. And this, when I say all, then some people are into finding counterexamples, and if you are into finding counterexamples, you will find counterexamples, but you'll have to engineer your Hamiltonian really, really careful. Okay? You'll have to go there and make strange things happen. And this, so maybe the statement is for all systems that we would consider of interest, before we started looking at entanglement, right? So if now that we're looking at entanglement, you come up with a system that is of interest because it violates this rule, that's fine. But if you would like to understand some typical condensed matter system, or in quantum field theory, we'll find similar behavior and so on, then you will find that there is this area law or almost logarithmic correction. So the evidence for this then comes from quantum field theory arguments of, take the continuum limit of this lattice and calculations. Actually, it looks like a subfield in quantum field theory to compute entanglement entropies nowadays, but also from exactly solvable models. And also from numerical calculations that of the type that we've been doing during the first week and the second week. Okay, and in particular, this logarithmic correction that we see in higher dimensions, say in d equal to 2, right? We see these logarithmic corrections. Then this, of course, has been seen in Fermi gas, which is this free fermions, but it also corresponds to Fermi liquid, which are effectively described by some Fermi gas, so no surprise there. But more interestingly, they have also been seen in systems of bosons, what's called spin Bose metal. Okay, you don't need to start with fermions for the ground state to be the result of some collective organization of degrees of freedom, which includes something that looks like a Fermi surface. Okay? And so spin Bose metals are examples of systems that effectively have some form of Fermi surface, and then they display these logarithmic corrections as well. Okay, and as I said before, ground states are not very entangled, so next week we'll go to this table, and we'll try to find a tensor network description, efficient tensor network description for any ground state. For each type of scaling, we'll have a different type of tensor network. Very good. So now, what I want to do is I want to investigate this. I made a list of behaviors here, right? And now we would like to start. I made a list of possible behaviors, and I explained why this might be relevant. But now I would like to start understanding why we have this behavior. And for that, I would like to understand why we have an area law. And for that, it's very useful to consider toy models. Okay? So that's what I want to do next. I want to talk about toy models for the area law so that we have an intuition of why we have it. And so for that, let me denote. So let me draw, or I'm going to draw stuff. So when you see this, I'm using that to denote a singlet state. Remember, this was a state which was 0, 1, minus 1, 0. Okay, it's a maximal entangled state of 2 qubits. And what happens? And then if I take this pair, so each circle denotes a spin, and if I now declare this to be region A, you know that rho A is proportional to the identity, which means it has eigenvalues. The density matrix has eigenvalues 1/2 and 1/2, and we already discussed that therefore the entropy in this case is equal to 1, which is 1 EBIT. Okay. Good. So now what I want to do is I want to generalize this simple setting to one where we have many such spins. And we have that they are entangled pairwise. Okay? And I would like to understand if, in this case, if I decide that this is region A, if I call this 4 spins region A, I would like to understand how much entropy is there in rho A. And for that, what I need to do is to realize first that rho A is going to look like, well, from from this guy, what we get is identity divided by 2, the density matrix of this guy, the first spin. Then we have this pair in an entangled state, so that's going to look like a projector, like this. And then for the last one, we have, again, a reduced density matrix, which is proportional to the identity. Okay, I just quickly draw the density matrix, reduced density matrix for region A, where this is spin 1, spin 2, 3, and 4. Then this is for 1, for 2 and 3, and for spin 4. Okay, I hope this is clear. So then if we look at the entropy of rho A, remember that we discussed briefly that the entropy is additive and the tensor product. So the entropy of these 3 objects is going to be the sum of entropies. And so that's going to be the entropy of identity divided by 2, which is 1. This is the one that we just discussed. Entropy of a pure state, which is 0, plus entropy of this one, which is, again, 1. And so if we add this, we get 2. Okay? And the rule is very simple. Whenever you see a drawing with singlets across, and you want to know the entropy of region A, you just count how many singlets you are cutting. Okay? We count how many singlets we are cutting. That's going to give us the entropy. Is that clear? Okay, the entropy being additive, it just adds contributions from every single singlet you are cutting. Very good. So here's my toy model. Okay, I'm going to assume that on each side you have a lattice, a 1D lattice. I have a 1D lattice, and each side is described by 2 such spin 1 halves. On each side, instead of having 1 spin, I have 2 spins. No problem there. And then, so this denotes one side, the next one, and so on. And then I have that each spin in this pair of spins is entangled with a spin in the next side. Okay? So you see a collection of singlets here. And now I want to understand how much entropy we have in this case. And so what I can do is I can consider region A to be like this. Okay, this is region A. And how much entropy do we have? 2, right? We are cutting 2 singlets. Okay, so the entropy for region A is 2. Now, I'm going to consider a larger region A. Okay, so let's call this A prime. And I'm going to ask you how much entropy we have in A prime. How much? Very good. So 2 sounds like a constant if it happens twice. This 2 really is 1 plus 1, meaning adding a contribution from the right boundary and from the left boundary. And what's happening here is that as we consider a larger and larger interval, region A, the entropy is only coming from the boundary, right? And the boundary is not changing. We are changing the bulk, but not the boundary. Okay? Okay, so we conclude that with this toy model, that indeed entropy as a function of L is going to be a constant. And in this toy model, this constant is equal to 2. And it's just reflecting the fact that we have only short-range entanglement, okay, entanglement between only nearest neighbors. And so it doesn't matter how large the region is, the entropy is only coming from the boundary. Okay? Sorry. Very good. So what happens next is that we're done with the toy model in 1 dimension, but this is already reproducing the area law, which is what we had for gap systems. And you can think gap systems, short-range entanglement, that makes sense. So that might be a very clear, intuitive picture of what's happening in the ground state of a gap system in 1 dimension. And now, this says turn page. Yeah. Now I'm going to delete all this mess here.
So what if the boundary cut through the circle?
What if the boundary cuts a side? Yeah. You don't want to cut a side. Poor side.
So we have in one side. We have 2
Okay, so you could, the important thing is that this is not growing with L. So if it fluctuates a little bit, we don't care. It's not that it's constant. It's that it's not scaling. Okay? So it's upper bounded by a constant if you want. Yes.
How the gapness of the system is related to the short range entanglement?
Are you asking whether this is the ground state of a Hamiltonian that is local?
Yeah.
actually, you could build some Hamiltonian that's for a local Hamiltonian for which this would be the ground state.
But like to see that the gap system should follow the area law, like we have to convince ourselves that gap system would have this kind of entanglement structure.
Yes, this is a toy model, so it's an oversimplified model, right? But you already got some intuition from it, and that's all I want. That you get some intuition. That indeed, so what we've seen here is this model leads to a constant entanglement, right? And now I'm just going to argue that, well, this is because it's short-ranged. So when you have short-range entanglement, the contributions that you have to count come directly from near the boundary, right? And that I'm just going to claim that this happens whenever you have a gap, that this happens in the ground state of a gap Hamiltonian.
Is a general argument why a gap Hamiltonian would have short-range entanglement?
You can build counterexamples, so I'm not going to say yes, right? But generically, that's what we see. And if you think that there is some effective field theory describing that, then you would think that it's a field theory for massive particles, so things cannot go far away, right? There is a decay attached to this mass.
Isn't there a general result that says that every gap Hamiltonian has exponentially decaying correlation function?
There is no general, again, you can always try to build counterexamples, but under certain assumptions, then yes, you can prove that there is some, under some assumptions.
Some reasonable assumption.
Yeah, if you ask me, they are reasonable. Reasonable and convenient. Okay, so let's jump to 2 dimensions. Okay, let's see that the same picture also, I mean, come on, I spent a lot of time drawing this, so let me explain it. That the same picture, we have something similar there. So this time, I ask you to consider sites with 4 spins on each side, okay? It's a toy model, don't panic. And then we have nearest neighbor entanglement between 1 spin here and 1 spin there, and so on, okay? And now, what you can do is, again, you can consider region, side region A, okay? And we are going to count how many bonds we have to break. And what you realize is that how many bonds you have to break is proportional to the size of the boundary of region A, okay? So in this case, we find for region A, we count them, entropy of A is going to be 2 per side. So there are 4 sides here, and each one contributes 2, okay? So that's equal to 8, very good. If we consider a larger region, say this region now, okay? So I'm going to call this new region A prime. So the entropy of region A prime is equal to 4 times, because we have 4 sides here, times, and now 1, 2, 3, okay? So we get some other number. What's important here is not the number, but how it scales. So if we had L time in a region that would be L times L, right? What we'll have is 4 times L, okay? And that's what we wanted. So we've seen that the entropy in D equal to 2 of this toy model, goes as is proportional to the size of the boundary of the region, okay? So area law, okay, that's what we call the area law. And why? Well, again, I'll argue that all the contributions come from spins that are very close to the boundary, because we only have short-range entanglement. So again, short-range entanglement implies this area law. All right? And then we could do the same in 3 dimensions. And so you could build some guy like this, right? Each side now has 6 spins, and they are entangled with neighboring spins. And then you'll get, again, that you have a region that is L times L times L, right? You're going to have some of these guys coming out. So you'll be cutting a number of bonds, which will be here. You'll get L times L, so L squared contributions, and then there will be 6 faces. And so this is going to be, again, S of L in D equal to 3. Okay, it's going to be L to the D minus 1 again. Okay? For the same reason. Very good. So conclusion, short-range entanglement implies the boundary law. All right, but we want to get also logarithms. And I'm so glad I already drew this in advance. So now we need to change the toy model. So I want to have another toy model. So now I want to talk about logarithmic corrections. And I'll start with D equal to 1 in one dimension. So now what I want you to think about is the possibility that we have not just short-range singlets, but also longer-range singlets. And in particular, we have short-range singlets between nearest neighbors everywhere. I'm just going to draw them near the boundary. So this side here is a very complicated object which has many spins, and I'm not going to even specify how it works. But assume that in particular there is a nearest neighbor entanglement here. Okay, nearest neighbor singlet between some degrees of freedom on this side and on that side. But also, if I now look at the system from, if I consider pairs of sides here and a pair of sides there, two sides together, there is also some factorization of the vector space here such that we get a singlet state entangled. So at some degrees of freedom in here entangled with the degrees of freedom in there, right? And the same thing here. Okay? And this happens also when we put together 4 spins inside and outside. We get a new contribution and also another contribution. Okay? So this time model is a bit more esoteric. I didn't explain exactly who is entangled with whom, but you can imagine that there are plenty of degrees of freedom in this Hilbert space for these two sides and these two sides, and that there is some entanglement between the two. So what we see here is that we have some, if we had some form of a scale invariance, then we would be saying that all length scales contribute to entanglement entropy, okay? And now it's just like, is that picture, it cannot be very clear, but is it kind of clear? But what I'm saying is that we go beyond the simple case where we only have nearest neighbor entanglement. Now we consider also entanglement at longer distances, yes?
So why exactly do we go from 1 to 2 to 4 instead of 1, 2, 3?
I want to consider some form of renormalization group transformation in which I rescale space by a constant factor, 2, and I want to do this several times. That's why. Okay. Okay, so let's look at this. So what we have here is that our region A has size 8, and we have, as before, that we just count contributions from the boundary. So we get the contribution that is equal to some number. Let me see. How do I want to explain this? Right. So what we got is the total entanglement entropy is equal to 2. This 2 comes from how many boundaries we have in a segment in 1D. But then we have different contributions. Okay. We get, in this case, 1 from this level, 1 from this level, and 1 from that level. Okay? So we got 3 different contributions from different length scales. Okay? If we had started with L equal to 4, then the entropy in this case would have been equal to 2 times how many different length scales can contribute. Okay? But in this case, we would see that there are only 2 different length scales, because you see here we have to stop. If we constrain this into a single side, right, the next contribution actually is entanglement that already goes across the system. So we had to stop. The size L of our region A is giving the largest length scale at which we will get the contribution from entanglement. So in this case, we would only get 2 contributions. Okay? If we had, in general, L equal to 2 to the n, then the entropy will be 2, it's coming from the 2 boundaries, times, and then contributions from all the length scales. In this case, we would have n different contributions, okay? N different contributions. And so this automatically gives us the 2 log 2, well, I mean, I would say 2n, which is 2 log 2 L, okay? That's how we get the logarithmic corrections. We have that the entanglement entropy between a region and the rest of the system is the sum of different contributions, each contribution coming from a different length scale. Okay, so I want to repeat this in 2 dimensions. Pedro, if you want to start using the blackboard. So I want to repeat this intuition in 2 dimensions. And in 2 dimensions, I'm just going to say the same, right? So I have, now we are in b equal to 2, and I'm going to consider a system of size L, in this case 8 times 8. And now what I see is that effectively, I can consider the time constraint this, and I'm going to count how many contributions to entanglement I get. But we know this one we know, right? How many? So the entropy here is going to be entropy. The total entropy is going to have a contribution from here, which we know from before. We have 8 times 4, right? 4 times 8. 4 is the size, is how many faces we have, okay? And 8 is the size, L, okay? So this is a contribution that we get from this, the shortest length scale. But now we can ask, okay, what if we also had contributions from longer length scales? So in this case, you know, if we constrain 4 sides into 1 here, right, then what we see is that effectively this now consists of only 4 effective sides. The length has been reduced. So now the contribution is going to be 4, 1, 2, 3, 4 times 4, okay? And here it's going to be 4 times 2. Okay? So now we're going to sum all these numbers. And what we see is that when we add them together, this is 4 times 8 plus 4 plus 2. But I could also write it in terms of 4 times 8, which was the original length of the boundary. And then factor 1 plus 1/2 plus 1/4. Okay? And in general, if you do this starting from a generic L, or L to the n, or whatever you want to consider, what you see is that you have 4 times L, okay, the entropy goes as 4 times L, and then you add contributions from all the length scales again. The first one comes with a 1, because you really have as many singlets as the linear size. But the second one, you have an effective number of sides which has been divided by 2, and the next one has been divided by 4, and so on, okay? And I don't even need to know how many terms. I mean, here in general have log 2 L terms, but the important thing is that they are not the same. And actually, if you add these guys together, you realize that this is always smaller than 2, okay? So this is upper bounded by 2, coming from here, times 4L, okay? And this is proportional to L. So what we see is that if we try to repeat the trick that we saw for this scale invariance trick in 2 dimensions, the entropy does not show a logarithmic correction. It's still Ario's law. Okay? But that should sound familiar, because what we saw here is for the gapless case is that if we have a small Fermi surface, okay, then there is no correction, logarithmic correction to the Ario's law. So is that clear? Okay, I'm counting contributions coming from different length scales, but this time the contributions from different length scales are suppressed because the effective boundary of these regions is shrinking. So we get that the whole sum is dominated by the first term already. Okay? Okay, so now what we would like to see finally is whether with the same type of toy model or a similar variation of the toy model, we can get the logarithmic correction. And the answer will be yes. And that's what we have here. So now what I'm going to do is I'm going to assume something weird. I'm going to assume that there was some form of RG transformation going on there when I was changing the scale by a factor 2. So I'm going to assume that there is, for some reason, when I coarse-grain my system, I get 2 effective copies of the coarse-grained system. Okay, so instead of getting just 1 copy, I get 2 at a different length scale. In other words, the contributions from the next length scale is doubled. Okay, there are more. It's as if the system had 2 copies, and then every time I coarse-grain, I get this kind of situation where each copy of my system produces 2 new copies. And actually, this is some crazy idea that came out of trying to match this logarithmic correction, but then you can go to systems and see that something like that happens, and we'll see this next week. In any case, when we do the counting now, what do we have? So first, we have contribution from this. The smallest length scale is 4, because we have, again, 4 contributions times L, the size, the linear size, and 1 copy. So now we're going to put here copies. How many copies we have? Okay? So this is, and this is the length, effective size of boundary. Size of boundary. And so in the next level, what we have is 4 times L over 2, right? Because effectively this length has been shrunk, divided by 2. We have 4 contributions. So we have 4 times 2. But now we have 2 copies, okay? For some strange reason. And we go down here and have 4 times 1 L over 4. What I'm saying is that each copy now is contributing. This L effective length has been divided by a factor 4. Okay? But now we have 4 copies. So now I think I can do this. 4L, 4L, 4L. So the total entropy now is 4L times 1 plus 1 plus 1. And this goes on for as many length scale as we want. Okay? So this gives us 4L log L. And this is the logarithmic correction. Question?
Yeah, what I really wonder about this is how these 2 different renormalization group procedures follow from the fact that the Fermi surface is small or large.
These are very good questions, and I'm not going to be able to answer them today. Next week I'll say the same thing. But let's wait there. But what we're trying to build here is some intuition, right? And the intuition is that the logarithmic correction in more than 1 dimension, so 2 dimensions, 3 dimensions, comes from the fact that something weird happens as we change scale. And this something weird, by something weird, I mean I mean that we get something like more copies of our system. Okay?
Is this used anywhere else in RG flows?
You've never seen this before?
Yeah.
Okay, good. Yes, no, there are papers about this. So I didn't make it up for this lecture.
I mean, for example, if I do RG flows in QFT, can I suddenly get these copies of my system? Or
QFT, if you work with the system with a Fermi surface, there is actually, this relates to holography. There is some holographic description where you will see an extra dimension that corresponds in the holographic direction, which corresponds to the number of copies. It's a continuum of copies. So you can relate this to holography. But I'm not going to do this now because Pedro is waiting. Thanks, Pedro. Sorry. Okay. We'll continue tomorrow. So it would be good if you have questions. Maybe we can address them tomorrow at the beginning.